For the next 3 mini lectures, we are going to be talking about motion and gravity. Gravity is an incredibly important thing for us in astronomy. Gravity gives the universe its structure. Gravity is this universal force that exists throughout the universe. It causes all objects to pull on all other objects everywhere. So there's always a gravitational force acting on you at all times too. And you are always exerting a gravitational force on other objects around you. Gravity is the thing that holds objects together, or at least it holds large objects together. It's responsible for holding the Earth in its orbit around the sun. It's responsible for holding the sun in its orbit around the Milky Way, and responsible for the Milky Way in its path within the local group. Remember, the local group is our local collection of other galaxies that are bound together by their mutual gravity. So this is a beautiful image that we call the Hubble Deep Field, and it shows a small region in the constellation Ursa Major. That's the Big Bear, and we can see a bunch of other galaxies here within this picture. So those galaxies are held together by the gravity of the objects within the galaxy, and then those galaxies are gravitationally pulled toward each other as well. Although gravity is invisible, it's an invisible force, we observe its effects. There are many invisible forces. Magnetic fields are an invisible force. Electric forces are invisible too. Everything with mass has gravity or experiences a gravitational force. The more massive an object, the greater is its gravitational force. So when I say mass, I'm referring to how much stuff makes up an object. How much stuff are you made of? A bigger object doesn't necessarily mean that it has more mass. You can have a very big object, can be as large as a room, but if the material that that object is made up of isn't very dense, then that object is going to have less mass. The more dense an object, the more mass it will have. You can pack a lot of material into a really small space, then you have an object that is really dense. Another thing about gravity is that it is an attractive force. That means it drags all objects toward each other. Okay, so for example, here we have the moon and here we have the Earth. The moon is exerting a gravitational force on the Earth. The Earth is exerting a gravitational force on the moon. Those forces want to bring those objects together, but we'll find out a little bit later why the moon doesn't just automatically slam into the Earth. It's because it has some velocity around our planet, and that what we call centripetal force of that of the moon orbiting around the Earth equals that gravitational force of the Earth pulling on the moon, and that keeps everything in balance. Now this is the equation for the gravitational force. There's an equation that goes along with it. So the gravitational force between two objects is equal to this big G here that we call the gravitational constant. It's a constant that's the same throughout the universe. And that's equal, the gravitational force is equal to this big G gravitational constant times the mass of the first object times the mass of the second object divided by the distance between them squared. And that distance is the distance between the very center of those two objects. And astronomers of antiquity did not connect gravity with astronomical motion. Galileo investigated the connection between motion and gravity with experiments using projectiles and balls rolling down planks. So if you're in my physics class, you got to experience this experiment in lab, where we had a plank here, we rolled a marble down it, that marble falls off the table and it executes a curved path that we call a projectile motion path. Galileo put science on a course to determine laws of motion and to help develop the scientific method. But before we talk about astronomical motion and gravity a little bit more, we need to talk about Isaac Newton and his 3 laws of motion. Isaac Newton came just a little bit after Galileo. Newton synthesized these ideas of motion and gravity into a few sets of equations that we use throughout astronomy and physics. The relationship between a force and the acceleration it causes was first understood by Isaac Newton. He outlined the mathematical treatment of forces in his work called The Mathematical Principles of Natural Philosophy. And that's this book right here. Sometimes we call it the Principia Mathematica. Newton identified 3 laws, that govern the motion of all objects. In the original Latin, these 3 laws only contain 59 words, so he was very concise with these 3 laws, but they still hold today. Newton's first law of motion is sometimes called the law of inertia. From observations, Newton concluded that an object will keep moving with constant velocity if no external force acts upon it. A body, or when I say a body, I mean an object, cannot accelerate, nor can it slow down unless it encounters friction or drag. So friction happens whenever you rub your hands together and they feel warm. Friction happens whenever you slam on your brakes in your car and the tire on your car rubs against the street. That's friction. And drag, when I'm talking about drag, I'm talking about like aerodynamic drag. The shape of an object can essentially cause a friction against the material through which it's moving, and that can help slow down the object too. So Newton's first law of motion says that a body or an object with mass at rest remains at rest, or if it is in motion, it remains in motion at a constant velocity unless it is acted upon by net external force. So an object in motion will remain in motion unless it's acted upon by an external force. Now, the tendency of an object to continue in its original state is sometimes called inertia. An object has more inertia if it has more mass. An object has less inertia if it has less mass. An object with more inertia is going to take more force to get it going. It's also going to take more force to get it to stop. So this is a classic example of an object that has a large amount of inertia. The train is very massive, it has a lot of mass, and so therefore it has a lot of inertia. And the wall of the building, this train station here in which that train was moving through, did not exert a large enough force on the moving train to stop it. And so because this train had such a large amount of inertia, it just went plummeting through the edge of the train station and fell out the backside. And this is an actual real photo of a real event that happened in Paris in 1895. For Newton's second law of motion, we sometimes just refer to the equation F equals ma. The force is equal to mass times acceleration. So acceleration is a rate of change of speed. So if something is accelerating, its speed is increasing every time step. Its speed is increasing every second if it's accelerating. If it has a constant speed, that speed isn't changing over time, then the object has no acceleration. And you can think about a force as a push or a pull. It could be any of those 2 things. So the acceleration of a system, for Newton's second law, is directly proportional to and in the same direction as the external force acting on the system, and inversely proportional to its mass. So here is the equation that Newton had in mind. Acceleration is equal to the force divided by the mass. That's what this sentence is essentially telling us. So if something is directly proportional, that means that when that quantity increases, the other quantity increases too. So if acceleration is directly proportional to force, if the force increases, the acceleration increases, and vice versa. If something is inversely proportional, that means that as one increases, the other must decrease. So if the acceleration is inversely proportional to the mass, we have to put the mass on the bottom side of this equation here for acceleration is equal to force over mass. So this says that actually, if our mass gets smaller, this quantity on the bottom of this fraction here, if that gets smaller, then the acceleration gets bigger. But if the mass gets bigger, this number on the bottom of the fraction gets bigger, then this fraction as a whole gets smaller, and so the acceleration gets smaller. So that's what I mean by inversely proportional to, okay? But usually we see it in the more common form that says that we rearrange this equation for, instead of saying acceleration is equal to force over mass, that the force is equal to acceleration times mass, or the force is equal to the mass times the acceleration, F equals ma. And the fact that it says that the acceleration is in the same direction of the force, acceleration and force are vectors. That means they have a size and a direction. So if the acceleration is in one direction, the net force acting on that object is also going to be in the same direction. And Newton's third law of motion says that forces must come in pairs. The third law of motion, for every action, there is an equal and opposite reaction. That's the way that I grew up remembering it. That's the way that I was taught in my first physics class. For every action, there's an equal and opposite reaction. You could be a little bit more specific and say that the mutual attraction of two bodies upon each other are always equal and act in opposite directions. When I'm talking about the mutual attraction, I'm talking about the gravitational force between two objects. But these force pairs do not necessarily need to be a gravitational force. They could be other forces too. Here we have an example of force pairs. We have two kids on skateboards. The girl is exerting a force onto the boy. The boy is exerting a force onto the girl. Those forces are equal in size, but opposite in direction. So eventually they're gonna push really hard on each other, and then they're going to push each other away. And because the boy was pushing on the girl and toward the left, whenever they push away from each other, she will continue motion to the left. And because the girl was pushing on the boy to the right, that force was directed to the right, and they push away from each other, the boy is going to continue off to the right, and then they'll be moving off away from each other in opposite directions because their forces initially were in opposite directions. Here we have an example of Newton's third law of motion that we certainly experience in Mississippi. For every action, there's an equal and opposite reaction. Here we have a mosquito that's gonna slam into the windshield of a truck. It's gonna make a mess. What is true during this collision? There's a whole bunch of options here. You can freeze the frame and read through them. But remember, Newton's third law, for every action, there's an equal and opposite reaction. That means that the mosquito is exerting the same amount of force on the truck as the truck is exerting on the mosquito. I know it seems weird, but it's true. So the answer here is A. The mosquito exerts the same force on the truck as the truck exerts on the mosquito. How is that even possible, you wonder? Well, remember that the force is equal to mass times acceleration. So they're both exerting the same force, they're both exerting the same mass times acceleration on each other. The truck has a big mass, the mosquito has a small mass. And in order for those forces to be equal to each other, that means that if the mosquito has a smaller mass, it's gonna experience the larger acceleration. If the truck has the big mass, it's gonna experience the smaller acceleration. So whenever they smush into each other, certainly the mosquito is going to be quickly decelerated to a stop. It's going to smush into the surface of the windshield. The truck actually does experience a small, but a very tiny deceleration in its motion because of that mosquito slamming into it, but it's going to be certainly not perceptible to you as you're driving your car. Along with those three laws of motion that we just talked about, Newton also discovered the law of universal gravitation, which we've already talked about a little bit. Every mass attracts every other mass with this gravitational force. The larger the masses, the bigger the gravitational force. The further apart these masses are, the smaller the gravitational force. So here we have two objects, mass 1, mass 2, and here again is our equation for the gravitational force. The gravitational force is equal to big G, that's our gravitational constant, is equal to mass 1 of the object times the other mass of the other object divided by the distance between them squared. This is an example of what we refer to as an inverse square law. That means that this force is inversely proportional to the distance between these objects squared. As that distance gets bigger and bigger and bigger, the gravitational force is going to get smaller and smaller and smaller by a factor of 1 over the distance between those bodies squared. These types of laws appear over and over and over again in physics and astronomy. We see them when we're thinking about electric forces, we see them when we're thinking about light intensity, and so on. With all that information, let's answer a few questions here about Newton's universal law of gravitation. Let's say we have two asteroids here, and they begin to gravitationally attract each other. If one asteroid has twice the mass of the other, which one experiences the greater gravitational force? So one's got a larger mass than the other, which one experiences the larger gravitational force? So remember here, to refresh your memory, is the equation for gravitational force. It's directly proportional to the masses of those objects multiplied by each other and inversely proportional to the distance between those bodies squared. So I'm going to show you a little simulation to help us understand this here. We've got two masses, mass 1 and mass 2, and I can change the size of those masses. Here we have these vectors, these arrows representing the gravitational force between these two bodies. So this arrow on top of mass 1, this is the force that mass 1 feels that's caused by mass 2. So the force on mass 1 by mass 2. And then here is this other vector, this other arrow, which is the force on mass 2 caused by mass 1. And you see that those forces are both pointing toward each other. This is an attractive force. These forces are equal in size. You see they're both 29.7 newtons. These gravitational forces that are being calculated between these two bodies are equal in size, but opposite in direction. And that direction, those forces are pointing toward each other. So if you didn't have something that was holding those objects in place, they'd want to accelerate toward each other. And here I have the distance between them, which is 6 kilometers. So right now, both of these masses are the same size, 4 billion kilograms. But let's see what happens when we double the mass of the second one. I'm going to increase the mass of the second one to 8 billion kilograms. So as I did that, the force, the gravitational force between those bodies increased, but they're still equal. They're equal in magnitude, but opposite in direction. They're still pointing toward each other, but those gravitational forces are equal in size. Newton is a unit of force. So if I talk about forces and you see that big N behind there, a Newton is a unit of force, and that was named for Sir Isaac Newton. And then let's see what happens. If we increase the distance between these two bodies, the gravitational force should decrease because the gravitational force is inversely proportional to the distance. So if I increase that distance, we see that the gravitational force decreased. If I decrease down to, let's see, here they're separated by 9 kilometers. The gravitational force between them is 26.4 newtons. And then if I decrease the distance between them back to 6 kilometers again, then the gravitational force between them increases to 59.3 newtons. So smaller distance between, the gravitational force will increase, and then a larger distance between the objects, the gravitational force will decrease. And then, so the answer to this question, two asteroids are gravitationally attracted toward one another. One of those had twice the mass of the other. Which one experiences the greater force? Well, it's a little bit of a trick question because we saw that they both experience the same magnitude of that gravitational force, same size of that gravitational force. So which of these two asteroids experiences the greatest acceleration toward each other? Well, it's kind of like that mosquito problem that we were talking about earlier, or Newton's third law. The gravitational force has to be the same. That means their mass times acceleration has to be the same. If one of them has a larger mass, they have to have a smaller acceleration so that those two forces equal each other. So the object that has the larger amount of mass is going to have the smaller acceleration toward the other. The object that has the smaller mass is going to have the larger acceleration toward the other. So which one experiences the greatest acceleration towards the other? It's going to be the one with the smaller mass.